Good afternoon. My name is Stephanie Trichler. These are my teammates Bryce Durham, Sherry Hall, Robbie Harris, and Evan Weiss. And we're presenting a project, Erebus. Erebus was a primordial Greek deity of darkness and shadow. It actually makes sense for our situation. Our main goal of this mission is to develop tools and technologies to allow humans to live long-term on other planets. This program provides a stepping stone to form permanent scientific outposts with human habitation of 6 months to eventually 2 to 3 years, and then hopefully eventually permanent colonies. To do so, this program would consist of 2 parts. We are focusing on the south polar region of the moon. This is due to the fact that the moon has a very slight axial inclination, and therefore the area near the poles has places of near permanent shadow. And these areas are thought to contain cold traps that have caught volatiles over the years, and thus scientists hope that this will be a place to find resources for moon bases. So phase A will consist of 3 exploratory missions. The first mission would be on the near side of the moon to the north crater rim of Shoemaker, which is right about here. This is because we're starting up a new communications net, and we want to make sure that we work out any sort of kinks in that, as well as any sort of issues with the new technology. Our second mission would be to the Shackleton crater, which is right at the south pole of the moon. This is the crater where scientists really think cold traps will be found in a lot of volatiles. The final mission would be to the South Pole Aitken Basin region on the far side of the moon. The mission could be to either the Zeeman crater or Schrödinger. This is because there has been scientific missions that have found olivine in near these 2 craters, which, as Marie Zuber told us earlier this semester, is thought to be lunar mantle material. Final determination of whether it's Zeeman or Schrödinger would come later after the first 2 missions, and also further technological analysis of the region. This is an illumination map of the 2 degrees right around the lunar south pole. You can see basically it's a compiled image from the wide-angle camera. And you can see Shackleton, the Shackleton crater floor has very little illumination. And up here you can see the Shoemaker crater. This is a brief timeline of our missions. It would start with the launch of the comms array, and once that is all set up, we have our 3 exploratory missions. Humans will be on the surface for about 2 weeks, which would be essentially a lunar daytime period, followed by teleoperated analysis, teleoperated rovers analyzing the area around there. Phase B is expanded down here. It's going to have a shifted crew rotation similar to what's going on in the ISS right now. Would start with the construction of the final lunar habitat, and then more people would come in, and science experiments would start up. Multiple science experiments can be run on a lunar base. The most important would be the effects of long-term low-G exposure to humans, but also the base would serve as a test bed for new technologies such as in situ resource utilization, attempts at closed-loop eclipse technologies, which would include tests on plant growth and that sort of stuff. There will also be a more detailed lunar geology lab on the base, and Cherry will discuss that later. So.
Hi, I'm going to talk to you about the launch and launcher architectures, as well as the different sorts of orbital transfers that we looked at for the project. Here you see a diagram of several of the different orbits we were looking at. Here's LEO. This is the International Space Station. It's at 52 degrees inclination, I believe. Here we have some highly elliptical polar orbits around the Moon. These Austin actually last year for 89 did a lot of work for examining the advantages of those particular orbits for plane changes. The idea being that at epicynthion it's much cheaper to perform a plane change than at pericynthion. So in a circular orbit at this same altitude, it would be very expensive to perform a plane change to get to a polar lunar orbit, whereas if you're farther away, it's much cheaper. So I have here on this diagram labeled L1 and L2, those being the Lagrange points. Some of you know a bit what those are. We'll talk about that a bit more in detail later. They're points in the orbit that is an equilibrium by the three-body problem between the Earth, the Moon, and the spacecraft. They are on, these particular two are on stable gravity manifolds. There's L4 and L5, which are unstable, and then L3 over here, which is also stable. The idea being we can perform a very low energy transfer from LEO over to L2 with this very curvy path and an Earth-Moon rotating frame, which is significantly cheaper than doing a direct transfer from LEO to the Moon. It is roughly a week the time it takes to actually do the transfer. So some options are to do a lower energy transfer to L1, meet up with a station that's in L1, transfer the station to L2. Moving between these particular two Lagrange points is very cheap, fuel-wise. So doing a lower energy transfer to L1 and then transferring to L2 is also an option. Both of those points have easy access to the lunar surface and also offer fairly good opportunities with phasing and launch windows to get to the point of the surface you want to get when you want to get there, and also to be able to get back from the surface. If you go to the next slide, we have a list of the launch vehicles. Why would we want to do these low energy transfers? Here you can see the shuttle and the Saturn V, which was used for all the previous vehicles, or moon launches, and the Nova launcher, which we talked about a bit in class. It was the proposed super heavy launcher that von Braun and his team were working on after Saturn. And at the far end of the scale, we have the SLS, which is currently being worked on at Marshall. It's also very expensive, the idea being that it would be about $3 billion a launch. We have existing launchers here, the extended extended expendable launch vehicles, the ELVs. So we have the Delta IV series, we have Atlas V, and this is SpaceX's Falcon 9 Heavy. These can also carry some fairly heavy loads. They're not man-rated yet, but if we send up several of these, which A, exist, and B, can carry fairly heavy loads, to LEO and the Lagrange points, we can establish refueling depots. So we send up fuel up there, which is a large portion of what would be contained in any launch for a lunar mission. We send up several of these rockets full of fuel and fill up an orbital fueling station in LEO at L1 and at L2. And then from there, send up a man-rated one of these with just the crew capsule, rather than one giant monolithic rocket that doesn't exist yet. If we go back. Yeah. Yep, thanks. The idea being we'd have a refueling depot somewhere around low Earth orbit, possibly next to the International Space Station for easy access if we have to assemble a spacecraft in orbit. One in L1 and another at L2. The advantage of L2 also, past all the lunar missions, is that it's a very high energy point in the Earth-Moon system. So it would be fairly easy to launch from L2, slingshot around the Earth, and get to the rest of the solar system without launching straight from LEO, which most of the current missions do. Talking a bit more about the utility of Lagrange points, we have Bryce.
So one of the, for any semi-permanent or extended habitation or exploration of the moon, it's going to require a more robust communication and navigation network than was used for Apollo. And one of the leading approaches to address this problem is the use of libration point or Lagrange point orbits, which are not actually orbits because they're not orbiting a body with mass, but they're more trajectories around this equilibrium point. The trajectories themselves are unstable and they require some station keeping to maintain the orbit. But as you can see in this diagram on the left side of the screen, there's 4 different trajectories, 2 of them on the near side and 2 of them on the far side of the moon. And basically these provide several advantages as compared to traditional low lunar orbits. They're all listed on the side. There's a few others, but one of the biggest ones is that a fewer number of these orbiters can provide the same amount of coverage as a larger constellation of pure lunar orbiters. And they also provide a great deal of flexibility as an expandable network that can be built up over time. They can be reconfigured at using very low amounts of energy, and in general they're more fuel efficient than traditional satellites, lunar satellites. So when it comes to, the last slide showed 4 satellites, or 4 orbits, and that would be essentially the minimum number of satellites required in these types of orbits to provide full lunar communication coverage. When it comes to navigation, the most traditional approach would be a Walker constellation. This is the foundation of the Earth's GPS system. The GPS on Earth uses currently 30 satellites. Nominally, it would be 24 in 6 orbital planes with 4 in each plane. For the lunar surface, because the Earth's GPS system is actually a modified Walker constellation, for the moon, it would only be necessary to have 18 satellites in 3 orbital planes. But there's actually an alternative to this, which is using these same Lagrange points. We can provide the same amount of coverage with only 14 satellites. And as I mentioned, that some of the flexibility of these types of orbits is that they can be easily reconfigured. And so something that can be done is that we can start a lunar navigation constellation with as few as 8 satellites, 4, as you see here, 4 on each side of the moon. And this would provide the basics needed for navigation for site-specific coverage and approximately 95% coverage of the lunar surface. And there'd be a few periods of time on the order of an hour where there would be insufficient satellite coverage to do complete positioning on the lunar surface. But it's a lot better for the early missions that only have very specific locations that don't have bases all over the moon. These satellites can be optimized to provide complete coverage for specific sites on the lunar surface. And then the advantage is that additional satellites can be added in the future, and this system can be reconfigured incrementally up to 14 satellites to provide complete navigation coverage on the moon.
Okay, now that we have some orbital assets to support our mission on the moon, we'll talk a little bit about how we'll get to the moon and what we'll do on the surface there. So as we embark upon this mission to land on the moon and send humans there for the first time since the Apollo mission, we want to use the legacy that we do have and build upon the success that we do have in our history of space exploration. So on the left, you'll see the Apollo 12 limb and some data from the Apollo 17 lander, which was obviously the last lander that we had. And on the right, you'll see the proposed Altair lunar lander, which is in conceptual design phase at NASA. So you notice a lot of similarities, and that's because obviously we're working on that legacy. We're building on the legacy that we have. There are some things such as technology miniaturization, advancements in material science, and environmental science advancements that are taken into account that are an improvement over what was available for Apollo. But perhaps the biggest impact that we have is just a change in operation. So for the Altair Lunar lander, which is much bigger, it's 27 cubic meters internal pressurized volume as opposed to just over 6 for the Lunar lander. We'll do a two launch strategy where we have an Earth orbit rendezvous and a lunar orbit rendezvous to support the larger lander. So we'll spend a couple of weeks on the surface in this Altair lander as opposed to up to 3 days on the Apollo lander, doing some science and evaluating surfaces. For the Phase B base, which is more of a long-term base. So design considerations for a long-term base on the moon, the most important consideration is radiation. That's the biggest danger to humans. So the way that we've decided to mitigate that risk is to use lunar regolith. We've got a design here that uses 2 meters of lunar regolith at 1,500 kilograms per cubic meter, which is enough to mitigate the risk of radiation. So just to sort of put that into reference, a full body dose of 4 to 6 sieverts of radiation is lethal for a human. The lunar surface can see 4 to 6 sieverts in specific instances up to 10 times a year. So that's sort of the motivation for why radiation is the biggest thing to consider. Other things are thermal protection, micrometeoroid impact. Both of those are also mitigated to some extent by the shell that we have. Again, this regolith is supported by a carbon composite shell, which some finite element analysis has been done to show that it can support that level of loading from the regolith at a lighter weight than, say, titanium or aluminum could. Again, this base will be built based on ISS legacy data. So once we have this base, that'll allow us to do some interesting science, which Sherry will talk about.
Yeah. So on our Phase B base, we're going to have a science laboratory set up. This will be used to analyze samples collected on EVAs during Phase B. There will be no regular returns to Earth during these phases, so it's important that we have a setup that can be used to analyze on site. It will include a basic geologic suite, including a thin slicer and a microscope in order to examine samples in a similar method to what you see in the images at the bottom. This kind of data will help astronauts decide if a given area they've been to during Phase B warrants further EVAs, second or third visit, to collect further samples. Okay, yeah. Now I'm going to go back and talk a little bit about ground operations during EVAs and how samples are collected during Phase A and how these samples are actually used to help determine Phase B base location. Crew on EVA are going to carry a science toolkit, it's seen on the left there. This is primarily composed of sample collection and geologic surveying equipment. The crew will have a lunar rover for transport just as was done on Apollo. But they are also going to leave behind seismic and lunar volatile collection experiments. These experiments will be left behind after the short stays to continue collecting data to help select what potential base location is most scientifically interesting. I'm going to talk a little bit about the L-VRAP on the next slide, but the seismometers are particularly important because they can provide long-term geologic stability data and also alert the crew to occurrences such as impacts. We will also include automated coring drills. These are robotic drills, but similar in design to the coring drills found on the later Apollo missions. Astronauts will still have to set these up themselves, which is fine because they will want to be the ones to actually select the sites to be drilled anyway. But by automating the actual drilling process, astronauts will be free to participate in more exploration activities, make observations, and make informed sample selection decisions that only a human on the ground really can. This is the Lunar Volatile Resources Analysis Package, or L-VRAP. It takes in volatiles from the local atmosphere and can measure the tenuous lunar atmosphere, as well as heat regolith and
taken those gases to determine volatile composition of the regolith on the moon. Again, these will be left behind to collect data at each Phase A site. Finally, we mentioned earlier that crew will have lunar rovers on EVAs. We learned in Apollo that having a vehicle is invaluable. For Phase A EVAs, a series of small recon robots will also be included on board. These are little robotic rovers that the crew can place in any areas they deem interesting or as potential construction sites. These robots will have cameras, be operated telerobotically from Earth in order to maintain a human in the loop, and also have a lunar regolith probe to check loose lunar regolith depth and determine evenness of the compact surface depth for construction. After base construction during Phase B, the robots, or an adapted version of them, will be sent out to provide kind of recon and information in advance of any human activity before the astronauts actually leave the base to perform an EVA. And on that note, I'd like to open it up for questions, and thank you for your consideration.
Yes, and let's use the mic so that we can get this recorded for posterity.
One thing that I wanted to ask is your constellation, that's for sort of GPS-style triangulation navigation and not just for communication?
That's correct.
Okay. And you're capable of providing that with only 8 satellites at targeted locations using the L2 and L1 halo orbits?
You're referring to the one that showed 4 satellites
Like
on
4 on each side.
Yes, that would be able to provide for a single satellite on in an orbit on either at a libration point on either side of the moon has about 90% coverage of the moon. So there are periods where there would not be coverage, but it can be optimized and targeted for site-specific to maximize site-specific coverage. So
Okay.
yes.
Great, thanks.
And
Another advantage we'd have on the moon versus the Earth's GPS system is we could have two-way communication between the ground node and the space node. On Earth, it's very much one way, but we can actually get timing information on the moon because there aren't going to be 50 million other customers trying to use the lunar positioning system at the same time. So,
what is your opinion of sending an unmanned surveyor mission before you do Phase A?
When it comes to surveyor missions, a lot of them are already in progress and a lot of them are already in the works. If we find that we can't get enough information at this point, I feel like we do have enough information from existing or planned missions like LRO, Chandra. We've had a lot of there have been a lot of international exploration recon missions that have looked at the South Pole region because it is of such interest. If in the planning we find that we are uncomfortable with something, then we could easily say, okay, let's delay. The moon is right there. It's not like we're working on a very specific time window like we would be for a Mars mission, where we only get one shot at sending people there every 20 years. Or not radiation effects. Yeah. So if we want to delay and actually include a reconnaissance, our design structure can actually support that.
You mentioned that after the initial 2 weeks, this is Stephanie in the introduction, you mentioned that after the initial 2 weeks of exploration with astronauts, there would be following 2 weeks of rovers. Was that correct?
It wasn't specified. It's 6 months to however long the rovers last. Okay. The area is still geologically interesting.
Okay. What do you see as the capacity or the limitation of using the rovers when you're in the dark?
Well, they would have to power down for the area. The L-VRAP, which is also going to be left behind by the astronauts, however, is designed to... It does power down during the lunar night. However, it has passive sensors that can pick up the lunar atmosphere, and then when sunlight returns, it can then process that sample that it's been collecting for 15 days.
So, but it could continue to collect in the dark.
Yes, it can continue to collect in the dark.
Stephanie, you mentioned in your first presentation that the aspects of the South Pole are in near permanent shadow. What does near permanent mean?
Basically, on very long time scales, certain crater floors don't ever see the sun. It's due to slight perturbations in orbits. For example, Shackleton crater floor might not have always been in shadow, but for the past probably couple thousand years at least, it has not seen the sun very much. There might be a little bit of reflected light from the crater walls, but not direct sunlight.
And then I forget if it was Evan or Bryce on the regolith covering the Robbie, the regolith covering the base. How do you propose to get it all up there?
So that'll be a telerobotic mission that we'll do. So initially we'd want to do that from an orbital position so that we don't have humans in harm's way if something goes wrong. I didn't talk about it a whole lot, but this is sort of envisioned as an expanding base, sort of like the ISS is. So for expansions where we'll have to add regolith shells, we haven't talked about that. We'd probably also do that telerobotically, though, to keep humans out of harm's way.
So there's like a telerobotic front loader.
Right.
Sort of thing.
Yeah.
So any thoughts on the cost of this mission architecture? I don't, did I miss?
So, I mean, I can't speak for all the different aspects. I know that they're for the launch and the communication and navigation satellite constellations, the entire constellation. So approximately, well, this cost actually doesn't include the 14 that we're proposing. It's more on the order of 10. But the launches and approximately 10 satellites would be on the order of $750 million. So that would include all the launch costs and the satellites and the operational costs over about a 10-year lifetime.
Seems kind of low.
The numbers I've seen for establishing refueling depots are usually on the order of $5 billion, which really isn't all that much more than a single SLS launch. And this would be multiple ELV type launches. As far as man-rating a rocket, I know that the SpaceX is working on that right now with their Falcon 9 Heavy, and I think ULA's been looking into it too for their heavy lift vehicles. I don't have a dollar figure to attach to that though. So.
And then I guess the other question was on the constellation of satellites. If you decouple GPS and communications, could you do the architecture for comms data relay with a much smaller number of satellites? I mean, is GPS really important in this architecture?
So if we were just interested in doing the comms, you could do something as simple as one satellite at the far side libration point, and that would provide approximately 90% surface coverage. And with the addition of one other satellite, you could provide full coverage of the far side. You could do the same thing on the near side with just 4 satellites with a few areas of no coverage, so one additional. So a total of 5 satellites would provide 100% coverage, so that you could have near side to far side communications. If you had somebody on the near side and somebody on the far side, it would not have to be relayed back to Earth to the other side. So yes, if you're just interested in communication, obviously you don't need the redundancy for the spatial positioning.
How do the science requirements?
Use the mic.
Okay. What positioning and navigation accuracies and other requirements are dictated by the science?
I don't have a specific answer to that. I don't know if either of you would like to.
Spitballing here, landing accuracy in the southern polar region could be tricky based on there's a lot of craters. It's lunar highlands, so you got mountains to worry about. However, the later lunar missions were able to land safely in such areas. So while I don't have a specific number figure, I think it would be easily we could easily make that little bit of leap to land accurately.
It would make the controls design for automated landings especially easy. With someone on board, we could steer around things, but with an automated landing, so delivering the automated forklift, the habitats themselves, the initial surveyors, it'd be much easier to deposit something if we knew where it was exactly.
You mentioned the advantage in terms of launching from one of the liberation points, over launching from Leo to go further out in the solar system. Give us any feeling for how large that advantage is, percentage, fuel cost, or any other?
I'd have to look it up.
Big or little?
Big advantage. Especially if the advantage of fuel depots happens when we use them often. If there's a continuous flux of fuel going in and out of these depots, so if they're used, just once or twice for a single mission, then it actually is more cost effective to launch a single monolithic rocket. But if we structure some of our other interplanetary missions around using these things for their Earth exit fuel, we can actually save quite a bit on earthbound launchers.
Let's get somebody from the Carrillo team up to set up your presentation, and then we'll have final questions. Okay.
This is a question about the lunar base. Do you guys have plans to make that sort of removable? Like when you're done with your moon mission, can you take any part of it with you for future missions, or the technology that you're using for it, is that going to be extensible to later, like Mars or whatever missions?
The technology itself will be, the idea is that it will be extensible to any foreseeable planetary surface that would be suitable for long stay, such as Mars. The base that we build within this project, the actual physical structure that is being built on the moon, we're referring to it as a semi-permanent base because the people themselves will not be there on a permanent basis from the point it is built forward. It does have a clear end, but the structure itself would be classified as a permanent structure, which would be ready for additions and provide an existing setup, kind of like the ISS in orbit, for future studies of humans in partial gravity or biological or lunar experiments. For any future missions, it would be an infrastructure.
This is maybe a stupid question, but for the communications relay and navigation aspect, how much can you save on that architecture if you just put a really tall tower at your base that can see over the horizon? It seems I can see some value to the navigation part, and you would need a GPS constellation for that. But if you're at a base, you know where the base is, and if you stuck a really tall tower on it, I don't actually know how tall that tower would need to be able to see the Earth directly. But would that be a way to potentially save?
Yeah, so I'll start off saying that's a really stupid question. I think the thinking of having a more capable system is that in the future we wanted to build something that can be leveraged going forward. So the idea that there could be additional moon missions beyond what we're proposing here, especially if there's multiple bases on the near and far side and not just at the South Pole, that there would be a lot of utility in having orbiting assets rather than having to build localized structures at each location. And conceivably you could have further exploratory missions from a base that would be of some unknown duration, that it would be useful to have something other than just a localized tower, for example.
Okay, let's go Erebus. Good job.
I have some papers I can see later about the price.
Okay. So hi, good afternoon. My name is Felipe, and these are my teammates, Nori, Jason, and Brad. And today we'd like to present Apollo's twin sister, Artemis, or America's return to exploration missions in space. Later in the presentation, you will learn why we've decided to choose the Powerpuff Girls to represent our mission. So, in order to return America back to its exploration times, and specifically the exploration of the moon, we wanted to look at a location with very high scientific potential. And we think that the Aitken Basin is such a location. Now, the Aitken Basin is known to be one of the largest, deepest, and oldest impact basins in our solar system. It is also believed to hold the key questions, or it's also believed to be the key to answer some of the key questions about our solar system. And so it is because of this great scientific potential that we would like to propose a lunar sample return mission to the Aitken Basin. Now, our team designed a mission that consists of 3 different phases to explore this particular region of the moon. The first phase will consist of delivering the necessary communication infrastructure to be able to do a mission on the far side of the moon. Now, the second phase, which is our primary goal of our mission, would be a manned mission that with the primary objective of collecting soil and rock samples on the Aitken Basin and sending those samples back to the moon for analysis. And phase 3, we think of it more in terms of a long-term project, where we plan on adding to the infrastructure that we deploy in the first phases of our mission for follow-on lunar missions that could potentially be of greater complexity and longer duration. Now, the next slides refer specifically to phase 2, so just please don't get confused with phase 1 and phase 3. As I mentioned, we want to explore the Aitken Basin, and so we wanted to select a specific landing site within the Aitken Basin. And to that end, we decided to turn to the NRC's list of scientific goals for lunar exploration. And in looking at that list, we selected 2 specific craters, just due to their scientific importance. And these 2 craters, as you can see on the screen, are the Schrödinger crater and the Amundsen crater, which are very close to the South Pole, and they're also very close to each other. In fact, they overlap by several miles. And so we think that this could be an advantage, as we could potentially explore both craters at the same time. Now, the next pictures and the tables show why scientists are very excited about exploring the specific craters. Just because there are a lot of questions that could be answered. In particular, the lunar cataclysm hypothesis could be evaluated, as well as many other things. Now, once we get to these craters, we want to make sure that the astronauts can move around properly and explore this area of the moon. So our team decided to come up with 2 different mobilization technologies. One will be the rover, which will be very similar to what was used during the Apollo mission, or the Apollo missions. And then a second surface mobility mechanism that we want to implement would be what we decided to call a hopper lander, which will basically give us the flexibility to get to those places where a hover will not be able to take us, just because of the geography of the moon and terrain. And in addition to that, this hopper lander will give us the ability to cover greater areas in a short amount of time. Now, in considering this hopper lander idea, we have 2 possible choices to choose from. So we have a ballistic hop, which requires significant planning in advance before you can do your hop, but it doesn't require a lot of fuel. Now, in comparison, you have the hover hop, which provides a greater flexibility to where we can go, but it requires more fuel compared to the ballistic hop. Now, so for our mission, we would like to have some sort of combinations of these different strategies, and then we would come up with an optimal trajectory just based on the terrain and the particular instance. So,
Okay, so Felipe mentioned we are going to the Aitken Basin on the far side of the moon, and there's a lot of challenges associated with that. First of all, there is no direct line of sight to the far side, so we are suggesting putting satellites in constellation. And because of the terrain issue and the distances that we're covering, we talked about using a hopping strategy in combination with rover traverse and manned retrieval of samples. The operation of the equipment is key. For our added equipment for this mission, we propose several launches, and we also suggest some recommendations and improvements in terms of equipment and strategy. Because this is our return to missions in space, for a long-term strategy, we also recommend using any margins that we have in terms of payload for in situ resource development. So just as, you know, a comparison between Apollo 17, this is the resource constraints that we're working under. We have similar operation strategy. We're using LEM to descend to the surface. We have the same amount of people for Apollo and Artemis. We're using rover traverse, and the differences between Apollo 17 and Artemis is that we are recommending about 2 times the sample size return. Even with this double amount, for the objectives of our science mission, we think it is better to have on-site analysis and make sure that we have efficient retrieval of the samples. So for the challenges that are associated with this mission, we propose a 14-day stay, and that matches the light cycle on the moon. The scientific equipment to achieve the objectives that we set out are similar to Apollo in that we'll need the same hand tools. For compositional analysis, we have X-ray fluorescent analyzers, and all of these equipment that we're bringing is on the lowest end of the weight and high portability. We also have for radiometric dating, we have portable spectrometers. And a net of 200 pounds is what we're budgeting for our total equipment over what we had in Apollo 17. The resource constraints that we mentioned earlier, about 14 days, 3 people, gives us a baseline of what we can calculate off of Apollo 17. So for the consumables of water, oxygen, and food, we were able to calculate a delta as shown. And we also have the extra equipment in terms of battery. We have extra scientific equipment of 200 pounds. The hopping equipment for increased structural integrity and the hopping capabilities, we're budgeting 2.2 kilopounds. But the bulk of our payload is in the terms of the fuel for this hopping. 31,000 pounds out of the total 36,000 pounds is budgeted for the hopping of the LEM. And that's for a cumulative of about 40 miles. And for 4 satellites that we're sending up for phase 1, we have a payload of 4,000 pounds. And any margin, as we said before, that we have, we would like to put towards the in situ resource development, basically our fuel, because any cost savings that you have there can save you huge savings in terms of payload. And for the budget that we have, we had a margin of about 2 metric tons, and this is what we see as a recommendation for in situ fuel development. And the total payload, or the total weight, is 21 metric tons. There's no way you can get that in one piece. So we're recommending that we bring in the front end of the process, the excavator and separator, which is about 1.8 metric tons, and we'll test the performance of each of these components separately. And Jason's going to talk about communications and navigation.
Okay. All right, so you see some similarities here from the last group, but for our column architecture, basically we want to use a fairly old idea that was originally proposed in 1971 about having satellites for communication relay in orbit around the L2 Lagrange point in the Earth-Moon system. So you'll have them orbiting on the far side here, and in such a way that they're at a big enough radius where they have basically constant line of sight to Earth assets. So looking from the Earth, you might see a picture like this kind of stylized image. Obviously, these orbits aren't as clean as this, but the idea is to have a constant line of communication to the far side and basically throughout the Earth-Moon system. The other thing about this setup is that the halo orbits have very specific orientations with respect to the Earth and Moon. So you can actually do fairly precise ranging with these types of systems, especially if you have multiple assets in that halo orbit. You can get down to a very small number of few meters in terms of position accuracy on the surface, which is going to be important for the traverses we have planned. The other thing about these halo orbits is that you can reconfigure the satellite constellations fairly easily. So on the bottom left is from a simulation in a paper that was released, showing basically going from a halo orbit in L2 to L1 and back and forth is really only a few meters per second delta V in terms of cost. So you can reconfigure it pretty easily. And then you can also, from the halo orbit, drop the satellites into a low lunar orbit, which does require a significant delta V to actually inject them into the low orbit. But fairly little to get actually out of the halo orbit to head that way. So as far as how we're going to get things to where we need them to go, for the phase one, for the satellite constellation, we're going to propose using a ballistic transfer, which basically looks something like this, where you fire it off from low Earth orbit out into space in such a way that the Earth-Moon's gravity pulls it back naturally into a halo orbit, and you actually don't require any injection burn when you get to the halo orbit, as long as you do the minor corrections along the way. This is very low energy compared to direct transfers, but it does take a long time to get there, but we're not terribly concerned about that since we want these assets up there for a long time anyway and check them out well in advance. For the remainder of the architecture, basically we're going to mimic Apollo. So this is from the Apollo 17 press kit, actually. So it's going to be very similar types of transfers for that, so we're not going to save a whole lot there, but this will actually let us get some satellites up there that actually have a very long mission life that can support further missions after this. So the launch system architecture, basically for rocket selection, we picked two rockets in particular that are in development, so they're not ready yet, but Space Launch System and the Falcon 9 Heavy, primarily due to the payload capability that they can give, and try to minimize the number of launches and dockings that we have to do in orbit. So ultimately, the architecture we came up with looks something like this. Basically, we're going to send the satellites to the halo orbit on a dedicated Falcon 9 Heavy, which arguably could be overkill, but we want to leave some margin in there for extra fuel and things like that, maybe added capabilities as well. And then we're going to send up the SLS with the human cargo for the lander and the CSM orbiter, and it's going to meet up in low Earth orbit with a couple of Falcon 9s that are basically fuel tanks. And it'll hook up and then take those along with them and use that fuel to get the extra payload down to the surface and also to do the hopping once we get to the surface of the moon. So now I'd like to turn it over to Brad, and he'll close out with human factors.
Okay, thank you, Jason. So looking from a human factors perspective, we wanted to go, as usual, to start with Apollo and understand what worked at Apollo and what people found after looking at Apollo retrospectively, what could have been improved. So hopefully everybody has seen this source, but in my opinion, it's the holy grail of sort of human factors assessment of Apollo. It's called the Apollo Medical Operations Project. It was conducted in 2005, published in 2007, and it reflects a study of Apollo 7 through Apollo 17 from a medical and human performance perspective. Everything that went well, everything that went poorly, and it culminates with interviews of 14 of 22 surviving astronauts who went to the moon. And stemming from all of this information and all of the analysis, 107 recommendations were yielded about how to improve the medical side and the human factor side of a potential return to lunar orbit or to the lunar surface. The prevailing attitude from this document, which is not really surprising, is that all future lunar missions should start with Apollo as a backbone. And only in instances where there are demonstrated weaknesses in the Apollo system should there be changes, whether that is technological improvements or actual organizational changes. Only where there are weaknesses that have been found in Apollo should we change the architecture because the architecture worked. So from that perspective, I'm going to talk to you guys about 3 different recommendations that we see that can make significant improvements to human factors operations on the surface of the moon. And the first one is radically changing the spacesuits that are used on EVA. We have a video here, and I'm going to hope that it works. I'm not sure if everybody has seen this, but I'm going to preface it. This is Jack Schmitt on Apollo 17, and he falls down. And he can't get back up at all. The reason for that is because he's in a gas pressurized suit. So I'm going to just play the video, and everybody pay particular attention to his knee joints because it's something that's very interesting that goes on with this suit. He drops his equipment. Dadgummit. Flips up in the air, falls down. And he rolls around for a while. It actually takes him about 30 seconds to stand back up. This happens several times on his EVA. The reason for this is because gas pressure suits act like springs. If you guys have ever taken a balloon and you've tried to bend a balloon, what happens when you let go of it? It springs back to its natural position. And spacesuits, which are pressurized just like balloons, act the same way. And so when Jack Schmitt tried to bend his knee to reach his equipment that he dropped, it's like bending a spring. And as soon as he let go of his muscles, the energy released and it flung him up in the air, and he couldn't get back up. So this is indicated in the Apollo recommendations that came from the document I was just talking about in several, in fact 12 I believe of the recommendations that are in the document relate to EVA in particular, and some of them that I want to call out are reducing the mass of the suit by a factor of 2, increasing general mobility of the suit by a factor of 4, and using a self-sealing pressure garment in the case of puncture. All of these things can be accomplished by using a different kind of spacesuit called a mechanical counterpressure suit. And for those of you that aren't familiar with it, it's a spacesuit that's skin tight. And you get pressure against your skin, which is something that you need from a physiology standpoint, but you get it from the interaction with the material instead of from being in a gas pressure bubble like the A7L suit is. It's not a new concept. NASA investigated it in the 60s, and that's what you see in the middle picture. It was called the Space Activity Suit, and it's just a giant elastic leotard, and it worked. They put a person in a full vacuum in the suit, and he was able to survive just fine. There were some limitations to the design, and it wasn't ready by the time that we wanted to go to the moon, and so NASA tabled the concept, and it's been tabled for 40 years. But if you were to use a suit like this, not only could you eliminate all of the mobility problems and satisfy the 3 recommendations here from the Apollo project document, but this plot down here demonstrates actually the amount of energy that it takes to operate in an MCP suit. The x-axis here is energy expended moving in your suit. And there's 3 different suits that are represented here. A mechanical counterpressure spacesuit, which are these little triangles right here, an unpressurized gas suit, which are these little carets right here, and a pressurized gas suit up here. So it should be pretty evident from right here what this means is if you wear a skin-tight spacesuit, it's about as easy as walking around in a floppy, unpressurized suit, as opposed to fighting a suit at every instance, which is what happens in a gas pressure suit. So, recommendation 1, we propose scrapping gas pressure suits and implementing skin-tight spacesuits for the purpose of greatly improving mobility on a surface mission. Recommendation 2, as we've seen in this class time and time again, landing on the moon is really difficult, especially when you're trying to do it with a stick by yourselves on the moon. We heard quotes from Buzz Aldrin saying that communications while landing, they were cutting in and out. It increased his workload incredibly. Neil Armstrong overcorrected when he was driving. He said sometimes he felt like he was out of control. He was over-controlling the spacecraft. We propose that with modern technology, you can do a landing entirely automated. And there are at least 3 entities currently in America that are working on this technology: Blue Origin, SpaceX, and even NASA, with their Morpheus project, which people are laughing because Morpheus exploded on its last try, but we're not going to talk about that. But with modern technology and with the type of computing power that you can expect on a modern mission, we think that landing can be done entirely automated. And in that event, you can drastically reduce the workload of the human operator during lunar landing, and you can greatly increase the safety of the system. Finally, recommendation 3, we are proposing an all-female non-military crew. The reasons for that are several. First of all, there has been modern research that's gone into 3-person functioning teams and determining who, broken down by gender, if you have a 3-person team, whether it's all men, all women, or some mixture of the two, is there any decrement in performance in the operation of those teams? And the answer is no. Unisex teams, whether they're all men or all women, function exactly the same. The only team, frankly, of those 4 types of possibilities that was shown to have a decrement in performance is a team with 2 women and 1 man. So I would not recommend that. But from this perspective, you could have an all-female crew and you could expect them to perform identically well to an all-male crew. So there's no reason to exclude them the way that they were excluded during Apollo. Secondly, like I said, one of the big things that we're trying to do here is to deliver a lot of equipment to the surface of the moon, whether it's in situ equipment or whether it's the ability to bring samples back to Earth. Mass is at a premium, as it is for any space system. So females, from this perspective, actually bring more to the table than men, because on average, women are smaller volumetrically and from a mass perspective than men. So we are proposing delivering an all-female crew to the moon to do the operations that could be achieved by the team there. Finally, what should the crew be composed of in terms of their training? Apollo, they were all military with the exception of Jack Schmitt, but there, again, is no reason for that necessarily. It was given that we needed to have an all-military crew because of the emphasis put on piloting the spacecraft. But if we work with the assumption that you can fly and do landings autonomously, suddenly being a pilot and having exclusive test pilot capability is no longer as important as it used to be. So we're going to look back at the Apollo Medical Project and see what they recommended for the composition of the crew. And one of the explicit recommendations from Apollo astronauts when interviewed is that 1 person on the team should be a physician. And the reason for that is because they encountered an enormous amount of small-scale medical problems, either on the surface or returning to Earth. Everything from headaches to constipation to nasal congestion to all of these things. And they had medicines available to them, but the astronauts were leery of using them because they weren't sure of the interaction effects or the side effects or how everything would work together and whether or not they would be able to perform their duties under medication. And so they struggled through it needlessly, and they recommended having a physician in the future so that they could actually have an informed discussion about how to treat themselves and the conditions that they experience. The other two...
Time to wind up.
Okay. The other 2 recommendations, a geologist and a planetary scientist, for the purpose of improving surface operations for sample return specifically. And finally, the last thing that we propose taking with the mass improvements that you get from having MCP suits or having a smaller crew, we propose delivering a 3D printing lunar regolith system to the moon, which are under development at ESA and even being considered by NASA as the way of producing structural elements in situ. They've never been tested, so we want to deliver one and actually test it. So the summary, we want to go back to the moon. We want to do some good science while we're there to understand more about our moon and about our history, but we want to use it as an opportunity to test and develop infrastructures for an extended stay on the moon that can be used as a precursor for deep space exploration.
Can I see your concluding slides? Question, John?
Well, I guess I'll start. I might be able to buy the all-female crew, but why is it all non-military? I didn't understand the rationale there.
So the rationale there is that the military justifications that were demonstrated for Apollo is piloting. You need to be able to be a pilot. You need to respect the command structure, and we want pilots. So we're limiting ourselves to military. And the flack that was given for even including 1 scientist was so severe from the from what I can tell, the ingrained culture of the astronaut corps trying to keep it as a military-only structure. So looking at what needs to be done on the surface of the moon, science is the #1 goal. And we actually had a conversation with Farouk El-Baz as a team. We interviewed him and we asked him if you could pick 1 person to be on the crew from a specific training background, what would it be? And he said a field geologist. I mean, it might be his own bias because he's a field geologist, but...
So you're saying scientists, not pilots, but, military versus non-military doesn't...
So we're coming from the perspective that coming from the military versus coming from someone who has studied science exclusively, that they will be able to make better judgments in the field from a science perspective. And it's up for debate.
But somebody like Katie Coleman, who's a science astronaut and a military Air Force colonel,
okay, so I think...
Exclude her or not exclude her?
No, I think that we're saying that people should not be judged as being from the military as being the prioritized crew characteristic. If you find somebody with the science skills who also comes from the military, I wouldn't say that they shouldn't be allowed, but the military skills should not be prioritized over the science skills, which I believe in Apollo they were.
For the automated landing part, like you put a picture of the SpaceX Grasshopper, but these guys at SpaceX, they have a nice flat and huge landing pad where they know they want to land. And with your automated landing, how do you plan to manage the situation like what happened in Apollo 11, where you realize that you are going to an area full of big rocks and you have to go elsewhere? How do you plan to?
So I think that there are a couple of answers to that. One, we expect that the gravity and terrain maps of the moon are much higher resolution today than they are at Apollo, so we at least have a better idea of what you would encounter when you get to a certain spot. If what happens in Apollo 11 happens where you overshoot by several miles and you just end up in a spot you didn't plan to be in, we're not proposing that the system be only automated capable. Obviously, I think that nobody would buy into a completely automated system without any type of manual override. And so piloting skills will be important, and we didn't get to talk about it much, but in the human factor section, we propose that everybody that's on the mission have extensive pilot training, which Jack Schmitt and all other science astronauts went through during Apollo, and the studies showed that they performed just as well as any other pilot that didn't come from a test pilot perspective. So we would expect everybody to be capable of piloting the craft, have the craft to have the ability to be piloted, but have automated be sort of the primary paradigm and only removed if you run into unusual circumstances.
We have the next group come up and just set up the slides.
I have two quick questions about your hopper. First of all, is it going to be like a separate vehicle, like an open air sort of rover type thing, or are you going to actually use your main capsule lander as the hopper? And two, how are you going to deal with dust blowback?
Right. So the concept, the first question for the concept is basically that the lander is going to be refuelable, essentially. So part of the architecture we had where we launched extra fuel tanks is basically to refuel that lander. So it would amount to the equivalent of refueling the descent stage, doing your hop, and then leaving with the ascent stage if you were to look at Apollo architecture. The blowback is an issue, and that's part of the reason we also threw in the ballistic trajectories as well as the hovering type trajectories, because it'll depend on the terrain what we actually can do and what the visibility is like. And you have the same issues on the actual touchdown like you did in Apollo with the dust blowback as well. I don't know that we have a better answer than Apollo for that, but that's the concept at least.
Okay. Similar question on a different take with you specifically cite having that hover capability. How do you deal with or take into account not just disturbing the terrain and kicking up dust that blocks your view, but actually disturbing the terrain and introducing contaminants to sites that you might want to look at?
Right, and those are all considerations that we have, and those two examples were kind of the extremes. And I don't know if we said it explicitly, but the concept is really once we're on the surface, we've got a week or so in the 2-week mission before we decide where we want to hop to. And during that time, with high-resolution imagery and terrain maps that we actually build while we're there, we can actually optimize the trajectory to get to a specific place. And all considerations factored in as terms of disturbing the terrain, the efficiency of the trajectories, all that stuff. So that would be actually determined while we're in the mission, halfway through basically, and we'd optimize based on that.
Is there a pronounced difference between the price of the MCP suit and the traditional pressurized suit?
In terms of price, the price goes into the R&D. I mean, the suit itself is made out of non-exotic materials.
Like the marginal cost.
Yeah. I think producing an additional MCP suit is probably much simpler than producing an additional gas suit because you don't have all the plumbing and you don't have all of the containment layers and things like that.
John?
So on the similar question on the GPS, the Halo architecture sounds interesting. And is that for comms data relay only, or is that a GPS also orbit? And is GPS really needed to do these missions? I mean, I know you have heavy automation, but could you have a heavy automated system that's GPS denied, effectively?
Envision something similar to that. It's primarily a comm system, but it's also going to do ranging, and because of the nature of the Halo orbits, a little bit kind of like I described, you can do between having a line of sight to the Earth assets and other spacecraft in orbit and the multiple satellites in the Halo orbit, you can get very precise ranging and positioning information off of that. So we
propose basically using that as our GPS replacement, essentially, but not necessarily a GPS system. Right.
Okay, Hip Hop Artemis, thank you very much. Okay. Brings us to, it's not Lunatic, is it? Lunartica.
Good afternoon. We're Team Lunartica. My name's Hosea.
I'm Austin.
Natalia.
I'm Oliver.
And today we're just going to talk about our mission. First, we're going to talk about our mission objectives, our mission architecture overall, how we're going to do the mission, what stages there are, how we're going to get there, how we're going to live, what we're going to do while we're there, and how we're going to get back from the moon.
All right, so first, going to go ahead and just kind of cover some of the objectives for the mission, both science and then kind of a catch-all category for other. Our objectives are taken from the National Research Council. Some of them should sound pretty familiar. We've heard a few of them before. We're going to start by testing lunar cataclysm theory and then trying to anchor the early Earth-Moon impact flux curve. The late heavy bombardment period is not totally fully understood. No impact melt rocks prior to about 3.9 billion years ago have been found. And so the idea is to test for the age of earlier impact basins to try to either, more support that idea or I guess basically derive a better understanding of kind of the initial phases of the formation of both the moon and the Earth, as well as some of the inner planets within the solar system. We're going to be looking at thickness of lunar crust and characterizing chemical and physical stratification of the mantle. We've got some seismological experiments that we'd like to conduct with some algebs while we're on the moon. Followed up with compositional state and distribution of polar volatiles as well. As we heard from the first group, there's some cold traps in the South Pole region that we think could preserve quite a few of these. Going to be inventorying just the age and distribution of the lunar rock types just to get a better geographic picture of what the moon is actually composed of. And we also want to take a look at characterizing the lunar atmosphere. There is a trace amounts of atmosphere on the moon prior to any more further human exploration, which could degrade what little atmosphere is left. We're going to go ahead and try to characterize it as much as possible, both from orbiting measurement systems as well as spectrometers that are ground-based. And of course, along the way, we want to figure out what 90 days in 1/6 gravity living on the moon is going to do to the human body. So we've got some experiments that are going to take a look at the effect on our astronaut crew as well. Other considerations are pretty general and basic, but we want to minimize cost. We want to take advantage of existing technology that'll help us minimize the cost. We want to prove the feasibility of a long-duration mission to the moon to set ourselves up for follow-on missions. And we also want to look at enabling remote and autonomous operations, not just from Earth, but also from the surface of the moon as well while we're there. In terms of how we're going to get there, kind of how the mission's going to look, I'm going to hand it over to Natalia to talk about our mission architecture.
Okay, so kind of a high-level breakdown of the mission components. First, we need to launch. We propose using 3 Saturn V launches to get to the moon. We're going to resurrect this technology. We also looked at the SLS, and if that becomes available during this time frame, our mission can be easily reconfigured to accommodate that using only 2 launches because of the increased payload capacity. But for now, we're going with Saturn Vs. A primary reason was the primary reason is because we feel that it's more cost effective, hopefully, to resurrect these, and then also the payload capacity. We need the really large capacity. You can see here the max translunar injection payload capacity for Saturn V is 100,000 pounds, and we have 3 launches here. 1 unmanned cargo launch and 2 crew launches with some extra cargo and equipment. And we need almost the full 100,000 pounds with each launch. So after launching, we're going to land on the moon. We have our first unmanned launch that will go ahead before the astronauts. That will place our rovers and most of the base and cargo at the landing site. And we'll also place 2 communications and remote sensing satellites in a stable polar orbit that I'll talk more about in a second. And then our 2 manned launches will follow after that. And they will be, they'll be heading to our landing site here, which we chose primarily because of the relatively flat topology and its proximity to some craters that are of interest to the science objectives that we'll talk more about. So once at the landing site, the base will be set up both autonomously and using the astronauts, and then they'll perform day-to-day operations like science experiments, and then after the 90-day mission, they'll return with their samples. No. Oh, sorry. Okay, so I'm going to talk now about how we're actually getting to the moon. We broke this down into the manned and unmanned launches. Manned launches, we're following a Apollo-style trajectory. We're going to enter a low Earth parking orbit, and then if we have astronauts on board, we would like to get to the moon as quickly as possible. So we'll be executing a free return trajectory that will intercept the moon and will burn to insert a slightly elliptic lunar orbit, and then we will circularize that while also doing a plane change to the plane of the landing site. Our landing site was at, I think, 44 degrees south, the inclination, so we do have that plane change, which does add some delta V. And then we'll do the descent to the landing site. So this is the manned launches. The unmanned launches, we can take longer. We don't have astronauts on board, so we can save fuel by using a more efficient trajectory. We decided on a home-in transfer, so we would enter the same low Earth parking orbit and then use an elliptical transfer trajectory to the orbit of the moon. We would enter an elliptical lunar parking orbit. At that point, we would do a plane change to the landing site plane, and then the equipment for the lunar base would be descended to the landing site, and then the spacecraft that is left in orbit would do another plane change to 56-degree inclination. And the reason for that is because we're going to place 2 satellites in that orbit that will provide our communication to the lunar base and back to the Earth ground stations. And a little more on those orbits. So a little differently than you saw with the other groups, we found some more recent work done on identifying stable lunar orbits. So there actually are some polar orbits that don't decay or don't perturb too much. This is a complicated problem to solve because you have the 3 bodies. But in a few years ago, Eli, I think, identified a stable polar orbit that could provide coverage to the south pole of the moon using its continuous coverage using 3 satellites. We propose using 2 satellites, which can provide near continuous coverage. This is a clip of one segment of the mission. You can see that most of the time the landing site has direct line of access communication from both satellites. Sometimes it's only one, and then there's about 25% of the mission where we have 3-hour gaps once a day. So based on that, we would need to plan our EVAs and things like that around those gaps in communication, but we see this as being a simple, low fuel means of providing communication to the landing site. Pass it over to Oliver.
All right, so once we get there, how are we going to live? How are we going to survive? What are we going to do to sleep on the moon? We decided to go with an inflatable concept. This was a structure known as a tuft pillow inflatable. They're square habitats. They're very modular. They're all composite fiber construction, which is of great benefit due to weight. Primary considerations for choosing it, like I said, it's lightweight. Some of the studies have been done, used like Kevlar 49 as a material. It's actually a semi-rigid inflatable structure, and so what that means is that within each one of these inflatable squares, you have an inflatable support structure that's made of a thicker material. So you inflate that, and it'll actually support the weight of the deflated structure itself, but then the actual living space gets inflated again. So you kind of have the 2 sets of structural components to it, the interior and the exterior. It is a modular design. You'll see we have an overhead. We're going to use 3 in series to provide storage space, living space, and then a lab space. And then it's got a high volume to weight ratio. Just the fabric itself only weighs about 195 kilograms per each one of these, and it gives you about 90 cubic meters of interior volume. However, you do need to add some additional support structures. We're going to be using an aluminum truss support structure made of both 3-chord and 2-chord aluminum truss segments. And those are going to support aluminum honeycomb that's sandwiched between pre-preg carbon plates. And the reason for this is we're going to use regolith shielding as well. And so in order to support the weight of a meter
regolith shielding on top of the habitat, you need something more substantial than just an inflatable. The regolith shielding, as other teams have discussed, primarily is going to provide us with radiation exposure. We're only going to be on the moon for 90 days. So we're going to go with a meter depth as opposed to 2 or 3 meters. But even something like a meter depth of regolith also helps to eliminate some thermal variations, which helps for the heating and cooling of the element as well. And then, of course, micrometeorite protection as well. It basically acts like sandbags. The nice thing about regolith and about the way our structure is set up, and Austin's going to talk about it more, is one of our landers has the capability of actually doing a lot of the excavating work for us. And so you can find, construction grade 1 meter cube sandbags essentially. You can basically fill those up with regolith, use them to stack up on the sides, build your aluminum support structure, and go ahead and use the rover, to actually shield the roof of your structure. Construction of this is fairly simple for those reasons, which is another reason why we went ahead and chose this inflatable solution. So just to give you kind of the idea of an overhead, you've got a storage, a living area, a lab section, and then both life support and airlock come off the lab section as well. All right, while we're on the moon, we can talk about some of the human factors issues as well.
Okay, so the first thing we're going to talk about is the spacesuit that we're going to use. We're actually going to plan to use the NASA Mark III spacesuit. It's quite a bit heavier than other designs, but it's justified for 2 reasons. One, astronauts can kneel. So that video that you saw before of I just fell down and I can't get back up won't really happen. It also helps with the fact that since these astronauts are going to be doing a lot of sample examination and sample retrieval, they won't need large, long grippers. Rather, instead, they can just sort of bend down and pick up a sample to look at it, pick up a sample and put it back down, and it won't be too much trouble if they, say, fall over. The other really, really important consideration here is that this suit has a 0 pre-breathe requirement. Now, normally, for most of NASA's designs, what you would need to do is sit in a large pre-breathe room for several hours to most of your day, do something in there to keep yourself busy. In the meanwhile, you're breathing all this air to keep yourself from having problems once you enter the suit. But since this suit has such an atmospheric composition that you don't need to do that, we've eliminated basically the entire space field used by the airlock up until a small area that you just sort of go into, put the suit on, and then go out. So that eliminates a lot of equipment costs. That eliminates the need to actually have a room where astronauts can work while they're pre-breathing. So that's pretty convenient, and that lends some credence to using the suit. Another thing we're considering is the work-sleep cycle. Since the SPA base will experience 14-day light darkness cycles, we are going to actually have the astronauts are staying there for longer than 14 days. We're going to have the astronauts keep a 24-hour cycle of wakefulness and sleep following mission control. Obviously, EVA will only be done during the daylight periods, and that'll be during the 14-day periods of light. But while there's darkness outside, they won't be going outside. Neither will the rovers be operating. They'll be indoors doing sample analysis. But we want to keep them there for longer than 14 days because we're doing some human factors work, checking how people adapt to like 90-day missions and basically long-term space habitation. We also thought of including a human factors clinic. Human factors clinic will be integrated with the onboard medical suite. They'll incorporate such experiments as balance experiments, things like bone densitometers to check how your bone mass is, checking your muscle mass, checking your strain, using strain gauges to check how your stretching goes. We're also using mechanical counterpressure suits as experiments, not as spacesuits, to see what the effects are when you're living and working in a 1/6 gravity environment, while some of you are wearing mechanical counterpressure suits and others are not, or maybe some to different degrees of counterpressure. We'll be monitoring health changes throughout the entire mission using this clinic and using the medical suite in its entirety. And we'll have few further details in the science section on some of the finer details of what we're going to do with this.
So during the surface operations portion of our mission, first of all, we're going to have 2 different types of rovers. We'll have 2 upgraded LRVs. We want to keep in mind the recommendations to keep what works. So we basically want to keep the LRV design, upgrade the batteries, maybe use some more efficient motors, and in emergency situations, make sure it's large enough to support 4 astronauts. We'll also have 1 athlete rover, which you can see here.
The idea being that the 2 LRVs would go together?
You basically have 1, so it's in the walkback requirement. In Apollo, we had the walkback requirement, and that was significant because if one of them failed, you'd have to be able to walk back before your supplies run out. In this, we want to replace that with a drive back constraint. So you go out no further than how far another LRV can go out and come bring you back. So with the Athlete rover here, it has 6 independent legs, and since each one of these legs can move around like that, it means that you only have to make the robot powerful enough to work in a much less strenuous requirements. So if it gets stuck, it's not really a big deal because it can just climb out. Also, each one of these wheels has a 1 horsepower motor in it. It has a shaft on there as well where you can attach tools like drills. Also, in this area, you can put on other attachments like a scoop to fill up our sandbags. And with appropriate batteries, this can basically be run 24 hours a day if you add on some solar power and large batteries. For our science portions of the experiments, first of all, we have seismology experiments we would like to conduct. So what we will do there is unpack and install ALJEPs, which are basically they're just upgraded LSUPs from the Apollo missions. We'd like to have somewhere between 3 and 10 of them. The more the better because you get a nice network. And the installation is really pretty simple and it can be done by a robot. The more complicated part is the unpacking of it. And that's where we think humans can really help with that. And if installation needs to occur after the astronauts leave, that's fine as long as they've unpacked everything. For atmospheric characterization, in our orbiters, we have the mass spectrometers on there, which will go and be able to just analyze and see what all is out there. And we will also have the 2, or at least 1 ground mass spectrometer, which will be near the base, and it can be carried around if they need to analyze the atmosphere around the base. And that also helps see how the area around the base changes as astronauts have been there for a while. For determining lunar formation, we'll also have sensors in our orbiting platforms, and those will be able to look at X-ray, gamma, and thermal emission spectrums. So that will help us just analyze, and we can tie that information later on with the samples that we collect and be able to identify and characterize those better. We'll also be doing sample triage with samples that we've collected through zircon analysis, which helps us identify the ages. So once you have the age combined with the X-ray and gamma and thermal emission, you can really start to put together a lot of information on those samples. While we're there, we'll also be doing exploration sample collection. Humans will be out during the day doing quite a bit of exploration and just trying to find out what's out there. And while the astronauts are sleeping, since we'll still have light outside, we can send the rovers out to do just some basic preliminary investigation to see if an area looks somewhat interesting. And those can be remotely controlled by people in Houston. And then be back in the morning so that the astronauts can go out and explore them more. We'll also be doing a lot of triage, so the humans can go and find samples that are useful when they go out there, do a little bit of triage, bring them back to the base, and whatever they don't need to bring back because they'll have 14 days to analyze them. For our biomedical laboratory, we want to measure balance, bone density, muscle performance, blood pressure, heart rate, and test urine samples. And this will help us just analyze and see what's going to happen to humans when they're spending 90 days on the moon. One of our mission requirements was to have a physician on board, so we will hope that they can go and make use of this information more than we would be able to. For our return, we are doing a hybrid LOR-EOR return. So the first thing we will do is have our ascent stages leave the moon, and they will go and dock with a service module. We do not have a command module at all because we decided it was unnecessary weight. And with our design, we will not have to use the command module to get back to Earth. So here, we'll refuel, make sure we have everything we need, and then travel back to Earth. At this point, we will dock first with a Dragon capsule, where we will put all of our samples and let that go back to Earth. And then each of our landers will, the ascent stages will dock with a Soyuz capsule. The astronauts will transfer into the capsule and then go down to Earth in the Soyuz capsules. And this avoids us having to carry a command module and the accompanying heat shield all the way to the moon and back, which we just found was inefficient. So it does require extra low-cost, relatively low-cost launches to do that, but we felt it was worth it.
So we realized that there were quite a few limitations and assumptions that went along with this kind of mission. Obviously, the first one that you all noticed was the reactivation of old technologies. Saturn V's, they exist, and the reason we chose them is because they exist. But there are significant reactivation costs to this, and obviously when you bring these things back up, people will realize, hey, There are probably problems here that we didn't see the first time, and probably something may not meet spec as spec is defined now. But obviously, these are going to be issues that are going to have to be resolved, but aren't really going to be within the scope of the report that we have here. The second is weight assumptions. So we basically did our analysis, as you saw in the beginning, comparing the weights that we're going to be carrying to the moon with a full capacity Saturn V. Some of that has to be reconciled a little bit with the delta V calculations, because that's going to be a driver for how we do our trajectories and whatnot, and the fuel burns that we actually have to use. And the last major limitation that we have is a difficult emergency return. Basically, the long-term and sort of extensive design of this mission makes it so that it's rather difficult to do a quick return back to Earth. It's not like you have everyone orbiting already and you can just do a quick burn and bring them on a free return back. Obviously, the setup cost required to actually return to the Earth is actually going to be quite a bit more than shorter term sorties. So in conclusion, Lunar is trying to outline a long-term 90-day mission that sends humans and robots to the moon, does a lot of geologic and other scientific analysis, and also in the meanwhile does analysis on what happens when you send people on, put them on the moon and have them live in a low gravity situation for 90 days. What happens to them? What happens when they come back? And what we're trying to do here is leverage as much old technology as possible, leverage as much proven technology as possible. You'll notice that very little of the technology that we're talking about is like completely untested. Most of it has either been developed and sent into space, or it's been tested extensively already on Earth. So that's sort of one of the main points that we're trying to emphasize here. And with that, we're going to open it up to questions.
For your, is this doing anything? Okay, I didn't hear it, so I wasn't sure. For your return, is it possible for your refueled lander to actually return to the ISS, or is it strictly necessary that you have to rendezvous with a Soyuz orbiter?
That was our original plan, to return to the ISS and use that as a base for moving everything out of the ascent capsules and back into the Soyuz and Dragon capsules. But first of all, it would require a plane change to dock with the ISS, and that's expensive in terms of fuel. If we're doing this directly, we can launch a Soyuz wherever we need it, and that's much easier than trying to move the International Space Station to where we want it. The other issue is that there are escape requirements for the ISS, so we would have to make a very complicated schedule of making sure that half the team on the ISS leaves, we get there. We'd have to add an additional dock onto the ascent module, because we'd have to dock a Soyuz to it before we're docking into the ISS, because you always have to have escape capacity for everybody on there. So we'd actually end up carrying quite a bit of extra weight just to be able to use the ISS. And this way we can just do a direct docking, and it simplifies things and it saves us some fuel as well.
It looks like you only have one lunar lander and you don't have a command module, so what happens in case of an emergency?
So a little bit of extra. We actually have 2 lunar landers, each carrying 3 people. And this is part of our weight assumptions, and what we're trying to do with our rockets is we have 2 human rockets, and each one carries 1 lunar lander. They have been, it's basically the Apollo lunar module, but expanded slightly to hold 3 people instead of 2. So in an emergency, what's going to happen is they'll have to get in the lunar module, get back up into orbit, refuel with the service module. They'll each have their own service modules, and then fly back to Earth. We'd have to do emergency Soyuz launches and then get them back down to Earth. So an emergency is pretty difficult to deal with there.
And then sort of another question, are you assuming in resurrection of the Saturn V that's instead of funding for the SLS? Or
well, we didn't really worry too much about funding. We're basically doing this on existing technologies and things that are almost done. We know the Saturn V works, and it has the weight capacity we need. The SLS, it might be nice to have, but we don't need it.
So it's again a question about the return. Because with your scenario, you say so you don't have to carry the weight of the heat shield all the way to the moon and back, but the counterpart is that you have, when you return, you have to perform an insertion burn in low Earth orbit. That will be probably very costly in fuel. And have you examined the, because like in Apollo, you don't have to do the insertion, you just go back to the Earth, like in straight line. Have you examined this trade-off?
No, we didn't look into that. So yeah, we did have a burn to get back into a low Earth orbit, but we didn't compare that to the cost of just doing a direct return straight to Earth. So that would be something to look into.
So I have a question regarding your cargo launch that you have that carries only cargo. You said you were using a Hohmann transfer.
Yeah.
Is there a reason why you chose the Hohmann transfer over something that's way more fuel efficient, like a Lyapunov orbit that Grail used? You know, kind of like that. It's on a, of course, much longer scale. So just curious why you chose the Hohmann transfer.
We did it basically for ease of calculations. A lot of these we did ourselves. And that was just easier to get an estimate for the amount of fuel we would need.
Why did you choose 90 days?
So we originally went with sort of what we found to be sort of longer term. What we wanted to figure out was, okay, we wanted to go with something that's significantly longer than anything that's been previously attempted. We figured that if you go for anything longer than 2 or 3 weeks, you would encounter this this lunar date-night issue anyway. And then after that, really, after we passed this whole 14-day, 28-day threshold, it was sort of arbitrary in going beyond that 28-day threshold.
Did you think that you could extrapolate from the life support systems and the human degradation that you see on station to apply to the lunar habitat?
So that'd probably be a little bit difficult because on station you're not really experiencing any gravity. But we expect that if you're living in 1/6 gravity, that your degradation is going to be it's going to be significant over a long period of time, but it's definitely not going to be as bad as if you're in 0G on the ISS. In the meanwhile, we also have mechanical counterpressure suits to see what happens, because that's a proposal that's being thrown around for longer duration space flights. So we're seeing basically what happens when everybody's in 1/6 gravity. What happens when some of those people are, in sort of strengthened artificial gravity with the counterpressure suits, and that doesn't really that's a little hard to do as an experiment over shorter periods, maybe a week or two. That's a bit harder to see than over longer periods, like we're proposing.
So I have a couple of questions about the spacesuits that you guys are using. So you're going with the Mark III, and it's described as being a zero pre-breathe suit, but that means that it runs at a much higher operating pressure, and with higher operating pressures means much stiffer joints in the suit. So as you saw in the picture of the Mark III, it's true that it is designed to have higher mobility in the hips because it has hard sections that rotate relative to one another, but the knee joints and the elbow joints are still soft materials. So do you really think that you're going to be able to kneel better in a suit that's at a higher pressure and still has soft knees, even though it's got better hip joints?
Well, that's basically the impression that we got from the reports that we were reading on it.
Okay, and the Mark III is also the heaviest spacesuit that's ever been made,
right?
And has a center of gravity that's at your upper chest level. Do you foresee any problems walking around basically as an inverted pendulum on the moon?
Well, when you put it that way, it'd probably be a little bit harder, yes.
And then the follow-on question about what I'm sort of confused about what you mean by studying the MCP suits. So you said you want some people in Mark IIIs and some people in MCP suits?
Oh, no. Sorry, that's not what we meant. MCP suits would not be used as actual spacesuits for going outside. It would be used for actually studying what happens when you're in counterpressure suits for long durations. When you're actually inside, some people might actually be wearing suits to actually counter the fact that they're sitting in 1/6 gravity.
So I guess I'm confused because it sounds to me like you're talking about intravehicular suits for countermeasures for physiological deconditioning. Is that what you are talking about when you mean a counterpressure suit?
Yes.
So that's different than an MCP suit. MCP suits are actual space suits. What you're talking about is probably like the gravity loading suit, which is what we work on in our lab. But those are spandex that you wear that are vertically shortened to give you sort of a musculoskeletal loading, and that's different than a spacesuit. It's more like underwear. But if that's what you're
Yeah,
talking
I'm pretty
about,
sure that's what we're referring
okay,
to. It would probably been useful to
okay,
have a
okay.
human factor specific person on the team.
Well, I'm gonna compliment you on the Dragon and the Soyuz as reentry vehicles. I've sat through a lot of different architecture studies, and I don't think I've ever seen that, and it might actually be pretty practical. The Saturn V coming back today happens to be the 40th anniversary of the final Saturn V launch of Skylab on May 14, 1973. Which I was actually there for that launch. But tell me how that's going to magically reappear. I mean, it's in museums, correct? But beyond that, tell me the issues associated with bringing the Saturn V back.
So there are a lot of issues. One of the things I've actually seen quite a bit about lately is we're trying to look at the F1 engines and find out how they work. Because we had them mostly figured out, but we're still not really sure of like the heat profiles and things on them. In addition, they were all manually welded by hand in ways that are no longer considered remotely acceptable. And everything today would most likely be cast. So there is a lot of work that needs to go into that. And they would need to be completely remanufactured. But since it has been done before, we can look through it and see like what are the basic ways we can speed up the process and do it a little bit better. And we feel like there's less engineering to do some minor upgrades than to entirely build a new system. But there's still a lot of work involved in doing that.
Other questions?
So regarding the fact that you're going to be operating during the 14-day dark period, I didn't see anything about provisions for electrical power or ECLOS power.
So for electrical power, we're planning on using the SAFE 400 reactor that NASA developed. Basically, we put on a nuclear reactor on the moon, and we get power. It provides 100 kilowatts of electrical power. We're actually looking at increasing that to about 126 kilowatts with our estimated power usages. And what that will let us do is run all the time. We looked at doing solar power, and first of all, we need a lot of solar panels to provide that much power. And we would also need about 125,000 kilograms of lithium batteries to hold power during the 14 days. So we decided that was probably not the most feasible option, and the nuclear system is about 1,500 kilograms, which is a little bit more reasonable.
How is that landed there? Is that part of the...
That's part of the cargo launch.
How are you going to get other countries to agree to allowing a nuclear reactor up in space of such a large size?
That's a problem for politicians.
That's also something that's been...
Now wait. Now what's the name of this course?
Well, just following up on that, what's the weight of the fuel that you need for that? How much? What is the fuel, and how much do you need for the reactor?
For the reactor,
radioactive.
I don't remember the exact numbers. I believe it's about 100 pounds. So the fuel is actually pretty light, and the whole system is designed to be passive when it's not operating. It was designed with political issues in mind. They've actually built some prototypes of it, and it's designed so that if you drop it in the ocean, it's completely passive and doesn't do anything. And it's not active until you go and make it turn on.
Thank you, Lunar. Okay, so we're halfway through. David, where are we? What have we learned?
Well, you guys have asked much better questions than we asked, so that's been good. Well, for one thing, I'm struck by the commonalities in the three presentations, which is good. Clearly means that there's some emerging consensus on what's scientifically interesting on the moon. And obviously we haven't read them yet. I will well, just as an observation, maybe to help some of the groups coming, biggest challenge I think they all have is integration among the team members, right? That you can sort of hear exactly what each individual's expertise is and interests are, and then the challenge is always how to bring those all together and keep the whole all together. So something to think about, and that's always a challenge in doing, especially the papers for projects like this. I don't know. I don't want to sort of prejudge anything because there's only half of them gone. We have 3 or 4 next time. 3 on Thursday. 3 on Thursday. That's good. So that'll leave us a little bit of extra time on Thursday too. Comments?
I'm very positively impressed with all 3. Good job on all 3, and in each one of them there was a surprise. Some a bit of a shock, but you weren't just doing Apollo on steroids, I felt that they were well thought out. So whether you came into this class already knowing everything, or you learned something from what we presented, it seems to have been effective. So
the flip side of that is obviously we didn't ask for Apollo on steroids. But then you sort of pose the question for someone who's watching these videos, how does a historical understanding of Apollo, like we've spent the semester on, help you when you think about designing future missions? And I think there's a pretty strong case in all the oral presentations, and I'm sure in the paper too, exactly what that is, because that was part of the assignment, obviously, but also every team drew on lessons learned from Apollo in a deep way. Not we sent 3 people there and then we're going to send 4, but how the projects work. With my opinion about the Saturn V, and Jose and I talked about this a little bit last week, but the hardest part about resurrecting is going to be the infrastructure, because all that's been dismantled, and they even gave away the launch platforms and all that sort of stuff, and we know how difficult and expensive those things were to create, much the less. There's an old story which you may have heard, which is apocryphal, that at the party at the end of Apollo, they gave away the drawings for a Saturn V, and we could never build one again. Which is, I don't know where that story comes from, but I do know it's actively not true, because I know the archivist in Georgia who owns National Archives the Apollo drawings. So, and not like there was one set anyway, that if you lost those, suddenly you were out, But that said, if there's one lesson of the class is there's a lot more to something like a Saturn V to make it work than there is to having the set of drawings. Even if you have a perfect set of drawings, it's still extremely difficult to replicate something like that, because there was so much. I think we watched the part about getting the nozzles in the F1 engine to work, which was pure, well, not pure, but systematic trial and error of like, well, it blew up again, let's go in there and tweak them a little bit more, get the combustion stable, and how many things were there like that, and how much craft knowledge was there in getting those stacks to line up and to get them to really go. And as we learned from Phil Scranton in the first couple weeks, they're a lot more like jewelry than cars from a Detroit assembly line, and they're really built, hand-built, one-off. I think the shuttles were probably that way too. Let me ask you one question. I think I did this last time, but I'm not thinking that straight these days. Did I give you guys the classes I'm teaching next year? No? Okay, so let me run down that for a minute, only because I want to take the chance to get free publicity and get people in the classes. And I don't actually have the numbers. Somebody might be able to write them down or look them up while I'm writing these down. In the fall, I'm teaching a course called Human Remote Autonomous Systems in ARC in Space, which is a graduate seminar. So it's not sort of lecture format like this. It's much more sit around a table and read books and look at studies and listen to people come in. And it's really a kind of, it's exactly correlated with a book I'm writing over the course of the next year, so it's helpful for me, which is the best kind of teaching. It's very hard to line your research and your teaching up really well, but this is a case where it'll happen, about looking at a set of issues that are common to extreme undersea, which is the world I've worked in for many years, aviation and space flight, about how you allocate tasks and what the issues are and how you operate systems in those different environments. And we'll actually go all the way back into the 19th century to look at factory floors, how people ran locomotives, a bunch of aviation stuff, some of the Apollo stuff which you've all been through, and then lots of other stuff around, how the A380 is flown, how some close looks at incidents and whatnot. It should be a lot of fun. So that's one. I'm not sure this is so relevant for all of you guys. I'm teaching the undergraduate human factors class with David Newman, although we're going to revamp that class altogether, and it's going to be called Human System Engineering. And it's going to be also a sort of slightly expanded look. Larry, I think, even created that class and then taught it for many years, and Missy Cummings has taught it, and David and I are going to teach it. So if any of you all are interested in that, many of you have probably taken the equivalent, all that. And then in the spring, also a seminar, which ought to be at least as much fun as this class, is, again, a graduate reading seminar on the history of aviation. That's, of course, I've been reading to teach this class for about 3 years. It's an incredibly huge topic, actually, once you really get into it. Also, it's going to, both of these classes are once a week, 3 hours. I'm not sure yet. They may not even have final papers. It's just the kind of presentation of the weekly seminar stuff. That's kind of typical for how humanities seminars are run. And in this one, we'll spend at least a week on just the Wright brothers and how they actually did their engineering all the way up through. And the number of ways you can cut this topic is just unbelievably huge. But it's also kind of looking ahead for the 100th anniversary of this department, which is coming up in a few years. Interesting, as always with these kind of anniversaries, you can count the origin of Course 16 in a few different moments, and then you just got to pick one depending on when it's convenient for the department to celebrate that centennial. And we haven't exactly decided, but it is definitely coming up. And so part of it will be some student-led research on the history of the department, which is incredibly interesting. And we were talking about this at your red team the other day. I mean, like McDonnell Douglas. Donald Douglas, graduate of this department, started one of the great companies, and McDonnell was too. And on down the list, the Wright brothers wind tunnel. Orville Wright was here to dedicate that wind tunnel when it was created. And so.
Okay, finally recall.
So sign up, please. I want you all.
Thank you, David. Okay, if there's anybody who hasn't signed the release form, try to download that and bring it in next time. Please do the course evaluations. They're valuable to us. We'll see you on Thursday.